Okay, so everyone can see my screen and everyone can hear me. Let's get started with today's topic about the uncertainty principle. Okay, so we're going to talk about this today. We want to derive this based on our knowledge of operators, and it's very loud. Okay, finally it stopped. Thanks. Let's hope it continues this way. We have seen the uncertainty principle already, right? In modern, if you have taken modern physics, you have encountered this already. And if I remember correctly, over there it was derived using Fourier transform, right? Prof. Ang told me that he used Fourier transform to derive the uncertainty principle. That was using kind of like the calculus way. Fourier transform is also something we did here, but it involves integral and calculus, and we have seen this before. But I will show you a proof of the uncertainty principle following the textbook of Griffiths, which is deriving using the concept of the operators, right? Which is a new tool that we are learning in this course. So if we are having a new tool, we might as well learn how to practice by using it in many different ways. So that is what we want to do today. So the uncertainty principle, you have seen, right? There are at least two versions you have seen before: X and P, momentum, position, and then energy, time. So these two things are different uncertainty principles, and what I'm going to derive today is for a general operator, because uncertainty principle, as we will see in a later chapter, is not just for position and momentum, but it involves other operators as well. One example, just to satisfy your curiosity for later, is that when we learn about the Stern-Gallac experiment, when we measure the spin, right? So when we measure the spin, we are measuring it is a measurement in the z-axis. Okay, so that is one observable. And then if we measure the spin in another direction, you have another observable, sigma y, sigma z, sigma y, and these two operators are going to have an uncertainty principle as well. Okay, so what does uncertainty principle, I keep saying, right? So let me remind you very briefly. Uncertainty principle, if you're measuring two quantities, you cannot measure two quantities with 100% precision and accuracy, right? It has to be some kind of uncertainty involved that is non-zero. Usually in your experimental lab, when you do a measurement, you have uncertainty. Usually it's because of experimental limitations, right? So if you measure a length using a ruler, you can't read the reading very well, so it's like not very clear whether it's 5 millimeter or 6 millimeter. So you have the plus and minus values, right? So that is the uncertainty. But it turns out that in quantum mechanics, even if you imagine the most ideal situation scenario, like no friction, everything in vacuum, everything perfect, when you do measurement also, you still get an uncertainty. But now we know it's actually not surprising anymore, because now we understand that quantum states come with probabilities. So when anything comes with probability, there's going to be having some kind of variance, right? You're learning about variance in probability and stats, I hope. Then the square root of the variance is the standard deviation, or when you're doing physics experiment, we call this the uncertainty. So there's going to be uncertainty just because quantum measurements involve probability. So that is what we want to understand today, right? So let me start by just stating the uncertainty principle. So it's kind of like a theorem. So the uncertainty principle is, like I said, right, is for any two measurement. It doesn't have to be position and momentum. So let's say they are A and B. So let's say A and B are observables. Then their uncertainties must obey this formula. So the uncertainty of A measurement, I'll just call this delta A, right? And the uncertainty of the measurement B is delta B. So delta A times delta B is always greater than some non-zero number or equal to 0, maybe, depends on the commutator. So it depends on the expectation value of the commutator between A and B. So this is the general uncertainty principle. In the case where it's X and P, then you get back your usual X and P formula. And if these two operators commute, then the uncertainty can be 0. But if it's non-zero, then the product must be greater than a non-zero number. So you cannot make both of them 0 at the same time. Okay? Or you cannot make either of them 0 at the same time. So this is what we want to prove in this entire section. So let us prove. Okay? So these are observables, right? So A and B. I want to derive this result. So let's start with the fact that they are observables. So since A and B are observables, what does this imply? Hopefully we are very used to this by now. They are Hermitian. So they are Hermitian. So what do I mean by being Hermitian? Means that the A dagger is equals to A and B dagger is equals to B, right? So they are Hermitian, and also they will have real eigenvalues, but we won't use this for now. Okay, so I want to calculate what is the uncertainty of this measurement, and to do this we start with the variance, right? So let's consider the variance of the A measurement, okay, is defined by, so are you guys learning the same thing in prop and stats? The variance is delta A is a something square, right? It is the expectation or the expected value of A minus the average of A, right? And this thing square. Okay, so there are actually two equivalent formulas. We will make use of both of them in several different scenarios. In fact, in the tutorial, right, I think it will be easier if you use this second formula instead. Right, so it's the expectation of A squared minus A squared. So this one is, especially in chapter 3 questions, some of them ask you to calculate the delta x and delta p for certain wave functions. It might be easier to use this rather than this, okay? But it depends. Actually, I don't know. I've never tried this before. Usually, I just feel that this is easier, so I just went straight to this. Okay, but in any case, let us calculate this quantity. So by the definition of expected value, right, it is some state. So for any state is given by A minus mean of A square and then this thing, right? So this is a bracket square. So bracket square, right, let me purposely just write everything out twice because it's a square, and we recognize that this itself is inner product between two vectors because A is Hermitian, right? So if A is Hermitian, then I could have written like A dagger, right? This is just a number, and this is just A minus A, this thing, okay? So in other words, what do I have? So just to remind you that this is Hermitian. That means this is one vector, and this is the bra of the same vector. That is the trick that we want to use. So I'm going to let this be equals, this is a vector, right? An operator eats a vector, it will spit out a new vector. It's going to be some vector, so we're going to call this alpha, ket. And therefore, this looks like the same thing, which is just the bra of this thing, right? So if you take the dagger, it will just turn into this. In other words, the delta A square is just the inner product alpha alpha, the bra-ket. Okay, so that is the expression for A, and I want to do the same thing for the variance of B. So similarly, right, what's the variance of B square? So the variance of B square is the expectation value of B minus B, the whole thing square. So you split this up, so you got B minus B, this thing B minus B, and bra of psi. And like I said, this is B is also a observable, so it's the same thing if I put the dagger there. But if I put the dagger there, then this is really the dual of this vector. So this, I'm gonna call this beta, and this is just gonna be the bra beta, which is just the dagger of this vector. In other words, the delta B square is equals to bra-ket of BB, beta beta. Okay, so everyone follow so far? All right. We are not doing anything special yet. We are just playing around with the bra-ket. We have been doing this for quite some time now, so I think should be no problem, right? But now let us, now this is why we use the knowledge of our previous courses, right? So this is why you guys have been learning linear algebra, where we are going to use one of the results of linear algebra here. So in linear algebra, you have learned something called the Schwarz inequality. Do you remember this? Okay. Wait, am I recording? Yes. Yes. Yeah, so if something actually got burned, then I will have to run away and we'll end the class, I guess. So Schwarz inequality is something you have seen in, I have asked your linear algebra lecturer already. It is, they told me it's chapter 5, right? Because I will just use this. It has been proven in chapter 5, I believe. So it says that, hang on, it says that alpha times beta, okay, is greater or equal to the absolute value of alpha beta. Okay, so I think in the language of linear algebra is like for two vectors, right? So the norm of this vector times the norm of another vector is always greater or equal to the product of this vector square, right? So this is the what you have learned, but this one is using our bra-ket notation, okay? And so we will make use of this formula. So this is alpha, my poor handwriting, this is alpha, right? And I want to manipulate this equation. So you see, right, there's a greater equal sign. So this is ultimately is going to somehow turn into our uncertainty principle, and it's just Schwarz inequality. So how to manipulate? What is this thing? So this is alpha beta inner product, okay, and then modulus square. And remember, these are vectors in Hilbert space. So when they are Hilbert space, if you take the inner product, this is going to be a complex number. Okay, so I'm going to let this complex number, since they're complex numbers, so we're going to call this Z. Okay, and I will use another identity involving complex number. So complex number, right, the absolute value of complex number is always greater or equals to the real part and the imaginary part. Okay, so I will have this identity like this over here. Okay, so if you're not clear, you can ask me later, but I will try to like at least get through the main concept because we want to prove the uncertainty principle, right? So maybe this is not very obvious to everyone, but let us put a pin on it, and we'll come back to this later. But let us believe this formula first, right? And how do I get a formula for imaginary number? So an imaginary number of Z is just 1 over 2i Z minus the complex conjugate of Z. Okay, so we have gotten this formula, right? And if I call this Z is equals to alpha beta, so this is alpha beta, and therefore Z bar is going to be the complex conjugate, so it's going to be beta alpha, right? So in other words, we have, so what do we have? We have alpha times beta is always greater or equal to this thing. And using this, we have also shown that this is also greater or equal than this thing. And what is this thing over here? So Z is alpha beta, like I said, minus this is beta alpha. Okay, so yeah, so we manipulated until we come to this. And then now let us try to simplify the right hand side. So this is getting close to our uncertainty principle already, because this is like delta A squared, this is delta B squared, right? So it has the structure already, but let us try to simplify this part over here. So what's this? Okay, so let's look at this thing. Let me simplify this term. So I'm gonna put it down here. Okay, and what is this actually? So remember, how did we define alpha and beta? Well, alpha was this thing, so this is my alpha, right? And then the beta is this thing. So the bra alpha is just psi A minus A. Whether got dagger or not doesn't matter, right? But this beta is B minus the expectation value of B, and then psi over here. Okay, so that was my B, and then let us expand this bracket. So this psi is AB, AB minus B operator A minus A operator B, and then plus A mean B mean, and then this thing. Okay, and then for the other one as well, wow, should I I'm making a mess, am I right? Yeah, so you do the same thing here lah, but this is beta alpha, right? So beta alpha is psi, and then I got B minus B, and then A minus A, and then psi, and then I expand the bracket, so I got BA over here. Remember, when they are operators, the who is front and who is back there's a difference, right? Remember, they sometimes they are matrices, or sometimes they are operators. They do not commute. They may or may not commute. Okay, so this is something where we have to be careful. So this thing times A, the bracket A is a number, so we can just shift it around. It's fine. But operators cannot move around. Okay, then what is happening here is this thing minus this thing. So let's take equation 1 minus equation 2, right? So equation 1 minus equation 2 is, it will give me alpha beta minus beta alpha, and then so these are the same, right? So everyone have the bra of psi on the outside, so I got AB minus BA. Okay, and then A with operator B, these two will cancel, right? And then this thing and this thing will cancel also, and this thing will also cancel. So everyone becomes 0. Okay, so in other words, I am just left with AB minus BA, and what was this? This is the commutator, right? So this is equals to psi commutator between A and B, right? So this is the commutator. So finally, we have figured out this expression now. So this is just the bra-ket. This is just the expectation value of the commutator, right? And we have shown that this is greater or equal to this. So let's go to page 3. Right. So we have shown that this alpha alpha, beta beta is greater or equal to something, and is greater or equal to definitely this has to be satisfied, right? 1 over 2i modulus AB what's the sound? Test. Everything is okay, right? So I hope there's no problem. So this was the variance of A square, and this was the variance of B square, and it's always greater or equals to 1 over 2i. And then this, what is this? This is the expectation value of commutator AB, right? So commutator A times B minus B times A, you will get a new operator. So if it's some operator, then you can do the bra-ket, then you can get the expectation value. Okay, so you got this expression. So everyone here is a positive number. Okay, and what I want to find is the uncertainty. So uncertainty should be the square root of A and B, and let's take the square root of both sides of the equation, right? So square root, if we take the square root of both sides of the equation, we have derived the uncertainty principle. So it's just 1 over 2i, the expectation value of A, B without the square. Okay, so this number is always greater or equal than this number, whatever this is. So we have derived the uncertainty principle between any two operators. Like I said, any operator A and B, it doesn't have to be position and momentum, but if they happen to be position or momentum, then we got the special case, right? So it depends on what is the commutator between the two operators. If the commutator is 0, so then there is no uncertainty principle, right? But if the commutator is non-zero, then you got the uncertainty principle, like the special case that we are very familiar with. In a special case where A is my position operator and B is my momentum operator, so what is the commutator between the two? I have shown you already in the previous class, right? X and P, commutator is just IH bar, right? And usually I'm too lazy to write the identity operator. Okay, so we got this. Then if we plug in our cases here, this is just the uncertainty in X, and then this is the uncertainty in P, and it's always greater or equals to the absolute value of 1 over 2i, and the commutator is just IH bar, right? So the commutator is just IH bar. Expectation value of identity, you just get just gone, right? There's no more square. So that's why we got delta X delta P is always greater or equals to H bar over 2. Okay, so we have now derived the uncertainty principle. Okay, so I think you have seen two ways to do it. In the previous modern physics class was done during using Fourier transform. We have done this again here using the concepts of operator and the commutator, right? And of course, these two are interconnected concepts. So there is a relation between concepts involving Fourier transform. You can translate this into concepts of operators, which is why both give you the same result, because they are actually talking about the same thing using different languages. Okay, so does anyone have a question? Okay, or is your brain burning already? Yeah, so that's the main concept about the uncertainty principle, right? And well, I guess I'll make a few comments. Let me paint a slightly interesting chicken and egg scenario. Like let us like think back on how we arrive at this uncertainty relation, because the way that we introduced this course, right? In chapter 1, we started from postulates of quantum mechanics. We define operators, and using that, we also define the momentum operators, right? So we started with momentum operator X and then momentum operator P. Okay, and in the way we did this course, I did not really explain the reason why momentum is defined in this way, right? So I just said, just trust me, let's go. Then we use the momentum operator. And after that, we done this, after we accept this definition, in the last class, last week, we have derived the commutator between X and P. We got IH bar. And because X and P do not commute, they result in an uncertainty principle. So got delta X delta P is greater than H bar over 2. Okay, so so this is our chain of reasoning that led to this. But like I said, right, sometimes in theoretical physics, you can think of things in a different directions. One way you can say that is that, okay, let's start with the opposite direction. Let's start with setting up quantum mechanics from the postulate that momentum and position do not commute. Okay, so if we start from here, then it will go backwards and it will derive because of this will cause the momentum operator to have this form, right? So it's a chicken and egg problem. It depends on which you start with, because if you for any theory in theoretical physics, you need to have some starting statement, right? So this almost like math, right? You have some axioms or some postulate, and then you derive the consequences. But if people want to do it the opposite way, if people want to say these are the postulates, and then you derive in the other direction. But in any case, you know, these are the some uncertainty. I mean, these are like the fundamental concepts of quantum mechanics. And in today's research, people try to people start to work on something which is called the generalized uncertainty principle. But I guess I won't show you much today lah. I'm just thinking about it because there's a new paper that appeared on arXiv today that what they try to do is to apply the generalized uncertainty principle to covariant formulation. Basically means the relativistic version, right? So yeah, so from here they start by this commutator, right? And then as you can see, P and P commute 0 and X commute also 0, and then they try to generalize this and derive some other concepts starting from that. But yeah, this is just to show what is happening for today's research. We're not going to worry too much about this. Just something interesting. So it's still an work in progress, right? People are still researching on it. It's not a closed old topic like Newtonian mechanics. So a lot of unanswered questions we still have about quantum mechanics. Okay, any other questions so far? Why is z squared greater or equal to this? This thing. Okay, so I guess, yeah, the one that we put a pin on it, right? So let's come back to this. So about this thing, right? So let's talk about this now. Okay. So about this equation star. Okay, so remember z is a complex number, right? So z is a complex number. It has a real part and then imaginary part, right? So, and then if it's a complex number, we can do the complex conjugate. And then we notice that if I take this minus this, right, is equals to 2ib. So the b itself is 1 over 2i z minus z bar. Okay, so this part was something that we use later in our derivation, but this b is defined, this b is the imaginary part. So this is imaginary z, so this is im z. That's why we call this im z, right? And what is imaginary z? So this is b. And another thing, the proof was the absolute value of z. So the absolute value of z is what? Well, it is this thing square. So this thing square means z times z bar, right? So if you calculate z, a plus ib, z a minus ib, so obviously you get a squared plus b squared, right? So we have shown that z squared is a squared plus b squared, and imaginary z is just equals to b. Okay. So you see this thing here, and this thing here. So from here we can conclude that because there's there's always an a here, right? So if I square this, it's just the square of this. These are just real numbers, right? So that's why it is always equals to the imaginary z square. Do you agree? Right? Because there's an a here. What's the brightness? And therefore you can also have a similar reasoning that it's also the same goes for the real part, because the real part is a, right? Then the real part is a, so a squared is always smaller than a squared plus b squared, right? So this is exactly equal if the a is 0. This is exactly equal if the b is 0. Do you get it? Okay. So yeah, these are complex numbers. Is a new type of number, so it will take a lot of the tricks are straightforward, but not obvious at first glance. Okay. Okay, so that was the uncertainty principle, right? And in the previous class also, there is another equation for uncertainty principle that was given to you, right? Which was the energy time. So what's the energy time uncertainty principle? It is going to be a different, so the equation kind of looks the same, but the fundamental concept is different. Okay, so let's talk about this for a minute. When we were talking about the observable uncertainty principle, it's like you're measuring A and then you're measuring B. You can't improve the accuracy or precision. I forget what's the distinction, but you can't make both of them 0, right? So when it comes to X and P, a simple example is this. Let's say you want to measure the position of an electron. Okay, so how do you measure the position of an electron as accurately as possible, right? Let's talk about position. Well, you want to see where the electron is. In order to see the electron, you need to shine light. But in quantum mechanics, light is a photon, is another particle. So the minute you shine the light, you are colliding it with another photon. So even though you can, because of the light, you can see the X accurately, but the collision will cause it to have a different momentum, right? So if you want to measure one thing, you accidentally cause problem in something else, right? And you try to do this in any pair of observables, it is going to happen anyway. Even though it's not so direct, but the theoretical fundamental relation is still there. Okay, so these are observables, and this only works when we have observables with Hermitian operator. But when we go to energy and time, right? What do we mean by energy and time? Well, this is supposed to be uncertainty of E and then uncertainty of T. So energy is the eigenvalue of the Hamiltonian. So we have an operator, but what is T? What's the operator? There's no operator, right? T is not an observable in the sense of quantum mechanics. Then there's no operator for T, right? So time is not an observable in quantum mechanics. Okay, there is no operator which we are calling T, right? We have never done this for time. Okay, time is just a value where you can, it changes over time, right? And then you look at the clock, but we can't really define an operator based on T. Okay, so how do we measure time in quantum mechanics? The way to measure time is by looking at the watch and see how another operator changes with time. That is the only way, right? Or at least one way. So let's consider some other observable. Okay, it's a bit of a, we are getting close again to the philosophical problems of quantum mechanics, right? Which I promise that we won't worry about it, but this is as close as we get. So how do we measure time? And this is actually a problem in physics. What is time, right? We use it everywhere, but we don't really know, you know, observable Q. Even in gravity, time, we claim that it's a coordinate, but if you really dig down to it, we are not really clear what is it. But we do know how to deal with observables. So let's consider an observables. The expectation value of the observable is, as always, we define it to be like this. Okay. Now I want to talk about time here, and like I said, the way to measure time is to check how another value changes with time. So I'm gonna say the rate of change of expectation value is something that we can at least write down, right? So this is the derivative of three things. So I will use the product rule. So how do I differentiate this? So by the product rule, I need to differentiate the first product, and then Q psi, and then differentiate the middle product, Q, and then differentiate the one at the last, okay, psi Q, like this. Okay, and for these two things here, we can use the Schrödinger equation, because this is the rate of change of a state. We can use the Schrödinger equation. Okay, let's start with the Schrödinger equation that we know, right? Psi is equals to h psi, right? So if I bring this over, I got the formula for the rate of change of psi, which is just 1 over IH bar, H operate on H psi. So if you take the bra of this equation, if you dagger this equation, then I got the rate of change of the state here, and then complex conjugate, so I got a negative sign, and then I got this, and then H, right? H dagger is H because H is Hermitian. So I'm gonna put this into here, I'm gonna put this into here, right? That's, yeah, I won't draw it too thickly to avoid making a mess. So that my rate of change of my operator is now, well, on this side, right? So on this side is minus 1 over IH bar psi HQ psi, and then let's put this here. So this is d dt, so this is just 1 over IH bar. So the constant, I can just shift it all to the front, and then psi q h psi, and then the middle one is still there. So the middle one is the expectation value of dt, right? So this is just the expected value of dq dt. Okay, so now we simplify this both sides. Well, we simplify this part of the equation. The rate of change of q is well, let me factorize the IH bar out, and I move the I up on top. Okay, so remember, I'm going to use 1 over I is negative I, and then I will factorize everyone outside. So I got the psi HQ psi. So if I pull out this thing, this will become a minus sign. So this is psi QH psi, right? And then this is the expected value of dq dt. And the bra and ket also, I can put it outside, right? So this is actually IH bar, the bra, and then HQ minus QH, and then this is psi. So this is actually the commutator between H and Q. This is dq dt, expected value. So this is just the expected value of the commutator times I over H bar, right? So this is HQ expected value plus dq dt. Okay, so now this one, it might be a little bit tricky. The d dt of the expected value is something plus the expected value of dq dt, right? So these two are not the same things actually, because what this equation is telling us is I have an operator, and I haven't said what this operator is. Maybe it is an operator that changes with time, right? So at time 0, the operator has some formula, and then at a later time, 5 seconds later, the operator changed into a different matrix or different formula. So if I want to calculate the expected value, I put the bra-ket, I got this. So this is actually an unusual situation, right? But this one is actually, yeah, it is an expected value, right? And I want to see how the expected value changes with time, like a position measurement. Position measurement also, in general, we do not expect them to be always fixed. Like for a moving particle, the expected value of position is, maybe it's at first is here, but later it's going to be at a different place. We have calculated a few of these before, right? But this one is unusual because almost all the operator we are using, the formula is a fixed formula that doesn't always change with time. Okay, it's independent of time until we go to chapter 7, but that's much later. So what I'm trying to say is we are going to assume for now Q is independent of T. So that dq dt is equals to 0. Okay, so then we have this formula dq dt. Average value of Q is, yes, IH bar commutator HQ. Okay, so I'm going to put this as the subject. Commutator HQ is equals to, bring this to the other side, so I got H bar over I, and then the rate of change of the mean value of Q. This is page 3, this is page 4. The next page is 5. Oops. Hang on. Okay. So where am I going with this, right? All I'm doing at the moment is just manipulating this equation, and the reason why is because, well, this is the same formula that appears in the uncertainty principle. So we do have an uncertainty principle between H and Q. H and Q, which says that the uncertainty in the measuring H and uncertainty in measuring Q is greater than 1 over 2I. And the formula, if I plug in H and Q, this was the uncertainty principle that we derived just now, before this. And we conclude that, well, this thing over here, if I plug in, what was this? This thing, firstly, is 1 over 2I. Then if we plug in, we got this. So H and Q is equals to this thing, right? So this is H over I. H over I dq dt. Okay. And then I times I is a negative, but negative absolute value is it will not affect our equation, right? We're gonna take the absolute value. Okay. So it's just h bar over 2 dq dt, right? And in fact, I will take out the h bar over 2 because these are just positive numbers. Okay, so this delta H, right? What is delta H measuring? H is the Hamiltonian. So the eigenvalue of the Hamiltonian is the energy. So what we're measuring for H operator is the energy of this thing. And this part is still the same. This is delta Q, but if I purposely bring this down, right, delta E, and then I got bring this the whole absolute value thing down. So this is delta Q, delta T, and then this is greater or equals to h bar over 2. Okay, so now we can see actually the time energy uncertainty principle is actually kind of like purposely define it in this way. I'm going to define this to be my delta T, and that is how we got the time energy uncertainty principle. It kind of feels like cheating, right? But there's a meaning behind this. Okay, so let me write this down. Okay, so I'm going to define delta T is equals to the absolute value Q divided by dq dt, right? So what does this look like? If I move this to this side, right, this is delta Q, and then this is absolute value d dq dt delta T, right? So this is the rate of change of the Q, and then I times T, and then I get the change in Q. So this is, like, roughly speaking, this is the time for the value of the mean value Q to change by 1 unit of standard deviation. Okay, so like I said, the reason why we come to this, it almost feels like, purposely we do it this way so that we have the energy time uncertainty principle that purposely almost looks like the position momentum formula, but the meaning of T is not time, is something that we can measure, but what we do measure are other observables, right? Other observables, and by looking at how other observable changes with your clock, you can kind of measure time in that way, right? So you can sort of like the time period where the average value of Q changes into something, then we get the we define this to be our changing by 1 standard deviation. So how long does it take for this to happen? We define this time to be the delta T, and this is the delta T that we have in our energy time uncertainty principle. So this is roughly 1 unit of time we can define in quantum mechanics. This is h bar over 2, right? So if you have read up about particle physics before, you might understand this is the you can have one of the consequences of this is, well, you can measure time very accurately by modifying this, or you can measure you can create virtual particles using this energy time uncertainty principle, right? So one of the consequences is like virtual particles. Do you know what is virtual particles? Right, virtual particle is like, let's say you're in vacuum, right? If you're in vacuum, then vacuum is by right supposed to be nothing, okay? And by conservation of energy, if there's nothing in the system, then there's nothing, right? Zero energy. But over here, okay, according to this, within uncertainty time t defined by this, you can have an uncertainty in energy. So, and this uncertainty in energy doesn't have to be zero. In fact, it cannot be zero. So if my energy is 0, right, it can be uncertain, plus and minus something. So if my energy is originally 0, within a short time interval, I can fluctuate this value of energy away from 0. If I can fluctuate away from 0, then I have a non-zero energy for a short period of time, right? And within this short period of time, and in fact within this short period of time, when you get energy, and you have learned that energy in special relativity, E equals mc square. So within this short period of time, I can actually create a particle of mass delta E equals to mc square within time delta t, right? So that means from here there's out of nothing, right? And then suddenly you create a particle, let's say a positron E, and then a negative E, and then go back to 0 again. Something like this. Okay, so that is how we have the uncertainty principle. Well, you can't, well, not to particle and antiparticle. So that is where a lot of like the interesting weird phenomena of physics can happen. Were you lost with this calculation? So if you're not sure, just you can ask questions later. But let me finish this line of thinking for a moment. It's very interesting. Again, another topic of current research, right? Virtual particles, within the time frame of delta t, you can violate the conservation of energy, something like that. And this is also back to research, right? This is kind of like one mechanism to explain the Hawking radiation. Okay, so without gravity, right, particle and antiparticle can like form out of nowhere and then vanish. Okay, but if this thing happen near the black hole, then one particle is formed and then one accidentally fall into the black hole, then you cannot recombine anymore. Then is permanently this particle cannot be disappear again. So does this violate conservation of energy? It does not, because this process will reduce the mass of the black hole, therefore reducing the energy, because this energy is stored in this other particle already. And because of this process, if you observe from far away, right, this is as if the black hole is emitting radiation, right? It's because of the antiparticle pair forming, one fall inside, the other come out away from the black hole. So we see this as a black hole emitting radiation, and the black hole keep on reducing mass. And therefore, eventually, if the radiation happen long enough, the black hole emission will be shrinking the black hole until it disappears. And that is one of the explanation of the information paradox, because when the black hole shrink to 0, then what happened to the contents inside? Right? There's some violation of unitarity in quantum mechanics. There's a unitary thing I mentioned before, but we haven't spent too much time, right? But again, yeah, this is just a interesting story to get you interested in like unknown questions. But again, we are not gonna worry about that for now. Yeah, right. This is like the this is because of this. Okay, so the chain of reasoning is because you know, in usually, right, usually in Newtonian mechanics, E is constant. But what was this? This is equation 3, right? But by equation 3, it tells us that this constant value can fluctuate by delta E within time delta T. Okay, so that means if I violate conservation, this one, it just means like a temporary violating conservation of energy. It might not be a very rigorous or accurate way, but at least it kind of like gives us a flavor of what's happening here. Okay, so this one, because this is E, right? This is E, so E is energy. It's supposed to be constant, but then what we are saying here, there's an uncertainty in E, right? You measure expected value, but sometimes it can plus delta E, sometimes it can minus delta E, so it's not always constant. But it must be within delta T, right? So it must be greater or equal to h bar over 2. It's not 0. So so this is you know, it's a temporarily violating conservation of energy, right? So within a short time, you can violate this. The shorter the time period, the more you can violate, right? So if that's why I will try to re-explain the creating particles out of nothing, since you were confused, right? So if energy is 0 in vacuum, there's no particle, nothing. Vacuum has no particle, so energy is 0. But within a short time t, it can jump from 0 to delta E temporarily. From 0 to delta E temporarily, then there's a finite energy. Suddenly there's energy out of nothing within the short time. Okay, within the short time, and this energy can form into a particle because of relativity. So E equals mc squared. This is how you create a particle out of nothing. Correct, yes. In some sense, yeah, 0, yeah, is 1 plus minus 1 in real life. So one particle and one antiparticle. Yeah, that's interesting, right? But in a more, how much time? Yes, I'm going to be break soon. So one last thing to add is, this is the most dramatic interpretation of, or the most dramatic application of this equation. But in a more mundane sense, right? Yeah, E is a measurement. There's going to be an uncertainty. So let's say if you're doing an atomic physics experiment, you want to measure the energy of something, right? And to reduce delta E, you need to increase delta T, because we need to preserve this equation. So this one is also important for like normal measurement. If you want to measure the energy level of a system, okay, so measure the energy level of some excited state of some atom, you need to measure it for a longer time in order to get the more precise value. If you measure something for a shorter time, then the value cannot be precise. So that kind of sounds like perfectly reasonable, right? The more you measure, the more sure you are of the measurement. The measurement process needs to take a longer time to get a precise energy. So that is like the more normal usage of the energy time uncertainty principle. Okay, so that's it. We have finished chapter 3. Uncertainty principle was the last topic, and essentially we have by now, right, in the first half of this course, we have established most of the basic foundations of quantum mechanics already. So these are the basic tools. Then in the next coming chapters, we will mostly be using the tools and teaching new tricks to solve problems in different situations. Okay, so after this is more towards applications and things like that already. Okay, any other question? So if not, yeah, let's take a 10 minutes break. So we come back at 10:06, right? So I shall stop the recording. Yes. This is page 6. So we're going to talk about the harmonic oscillator. Okay, so harmonic oscillator is going to be one of the most important topics, actually one of the most important topics in physics, because almost every theory of physics has an example involving the harmonic oscillator. So it is the simplest problem, but at the same time it is having a lot of rich physical behavior that reflects a lot of the physical properties of the theory. So this is one of the most important chapter that you will learn. Okay, so the harmonic oscillator. Okay, so we're gonna get started with that. Let's check any question. Yeah, right. Good mic. Think way better than mine. Just now I was checking the recording. The ringing bell was not captured in the OBS video. At least it wasn't very clear. Okay, so we are going to talk about the quantum harmonic oscillator. And quantum harmonic oscillator, I will understand that it's a bit difficult to imagine. So in the first part, it's not very mathematical heavy yet. First part, we just want to understand the intuitive meaning of the quantum oscillator. Okay, because this chapter, right, is going to have a lot of heavy math again, and you guys your brain will melt and explode everything again, like you guys will say when there's a lot of math. So to make ourselves ready for that, let us just understand what is actually happening. When we're doing math, most of the time we always forget what is the physical problem that we're solving. Well, this is an oscillator. So in Newtonian mechanics, right, we have done this in the mechanics class. We have a spring attached to a block of mass m, right? And then if this is an equilibrium position, the spring will bounce back and forth according to Newton's second law, right? Newton's second law combined with Hooke's law. And the potential energy of the system we have also derived in the mechanics class. It is given by half kx squared. Okay, so this is the basic picture of an oscillator, right? And this is the picture for the Newtonian. But for quantum mechanics, obviously we no longer have springs anymore. Quantum mechanics, we're talking about small particles like atoms and molecules, right? So how do we define an oscillator in quantum mechanics? Basically, any system that satisfies this potential energy. Okay, so this is what we call a harmonic oscillator in quantum mechanics. Even though there's no spring in quantum mechanics anymore, basically any system with potential energy that is given by some half k is a constant. So constant times x squared will be considered as a harmonic oscillator. Okay, so why is this true and why is this important? The reason why is because almost every system near the ground state is approximately this equation, this harmonic oscillator. Okay, so yeah, I'm gonna write this now. Even for complicated potential energy functions, well, we have solved a few potential energy functions in chapter 2 already, right? But for complicated ones, for the smooth ones near the minimum, which is what we call the ground state, it behaves like an oscillator. Right, so let's say, like, let me draw some random potential energy function. Okay, so let's say it's a continuous smooth function, right? So whatever this function is, this is the minimum of the energy, right? So if I take my energy level to be around here, this is the ground state, right? And let me choose, let's say this position is x equals to 0, right? So this is my function v of x that is near to 0, right? And let's consider whatever this value is. Let us solve a Schrodinger equation near the energy E. Well, we're not going to do that, but let's look at the potential energy function. So near the minimum, right? Near x equals to 0, we can do the Taylor expansion. Right? So my v of x is approximately v0 plus v prime 0 x plus half v second derivative 0 x squared plus dot dot dot, right? So with increasing powers of x. I'm recording, right? I'm recording. Oh, no, I think it's just nice. Yeah. At least the voice, the important part is you capture the voice. So your voice volume is perfect. I think it's just nice. So we do a Taylor expansion near the minimum. So this is the minimum, right? So this is the local minimum of the function. So that means this term is equals to 0. So therefore my potential energy, right, this is a constant. And then I got plus half v double prime x squared. Okay, and then plus the negligible terms, as long as I am near the minimum. So as you can see, right, even you have a complicated system, any system naturally will look at the ground state, and anything near the ground state, it behaves close to an harmonic oscillator, right? So this is like half kx squared, right? So in other words, most physical system okay, in fact, this is quantum or Newtonian, whether it's quantum or classical, right? They behave like a harmonic oscillator when energies are near the ground state. Okay, so this is why harmonic oscillators are important in everywhere in quantum mechanics, everywhere in physics, not just quantum mechanics, because most systems actually, you know, if we wait for it long enough, everything settles down to the ground state, and near the ground state, the function looks like half kx squared. And if it's near like half kx squared, then we can just treat this like we can carry over our harmonic oscillator solution. So even though when we started, you know, high school, right, even if you don't take mechanics with me, in high school you solve this problem, but this is a template of many situations, similar to many situations that we encounter in physics. Okay, so that's the general situation for the harmonic oscillator. Well, not to say this lah. Yes and no, actually. Yeah, it is the modern physics is the use addition, right? So you see this, and then in QM1 we encounter this again. But now, what is the main difference now is we are learning bra-ket, right? Hilbert space. So we will solve this using Hilbert space. But again, let me finish by remember what we are solving is there's gonna be a lot of math later, but I think it would be good to keep in mind actually what system are we solving. So let me just give you an example of quantum harmonic oscillator, right? So we know Newtonian harmonic oscillator, we know what it looks like, just the mass attached to a spring. But what about a quantum harmonic oscillator? The example will be atoms in a solid. Okay, so atoms in a solid, what does it look like? Let's say a solid structure, you have atoms arranged in some square grid, right? So maybe something like this, just a random example. Okay, so if I look at one atom, right? So if I look at one atom, let's study the displacement of this atom. Okay, it is going to be displacing. Let's look at the displacement in the x direction. So let's say x is equal to 0 is the equilibrium position. Then due to the forces interaction between other things, it's going to be very complicated, right? Like I said, even for complicated potential energy function, it's going to be some complicated mess. But if it's if the energy is like ground state, if it's low energy, near the ground state energy, it is going to have this potential energy function. So this is half kx squared, right? So the potential energy function, this is the potential energy function for this atom. Okay, so yeah, we are really talking about atoms now, right? These are not springs, but these are just the interatomic forces between these two objects, and it is a complicated function, right? And in fact, it's too complicated for us to handle here, but maybe the chemistry people will know the full formula and things like that. But near the ground state is approximately this kind of thing. Okay, yeah, so so we are going to express our harmonic oscillator in the following way. So in this chapter, this k, right, instead of writing k, it is more convenient for us in quantum mechanics to express, instead of writing k, we have k is equals to m omega square, where m is the mass of the object, of the particle, and omega is a constant. Okay, so this is because notation from from the Newtonian case, right? Remember in Newtonian case, F is equal to negative kx, and then this is equal to ma, right? And then a is the second derivative of position, so we end up with this differential equation where this is negative, dx dt is negative k over m times x, right? So we solve the solution where x as a function of t is equals to a cos omega t plus b sine omega t, where omega is the square root of k over m, so that my omega is or my k is just omega square m, right? And it is our constant. Okay, so therefore so in other words, the potential energy function of my harmonic oscillator is gonna look like this. So the potential energy function of the harmonic oscillator is given by v of x is half kx square, so I'll write this is m omega square x, right? So this is the potential energy function, and remember, when we want to go into quantum mechanics, we change this into an operator. So the PE operator for quantum mechanics is, I will just change my position x into the operator x, so it's just half m omega square, x square, right? X square, so this is the position operator of Hilbert space. So this is the harmonic oscillator that we want to solve today. Okay, what page is this? 6, page 7, page 8. Is there time? Yeah, there's about 6 minutes left. So there's two, so the quantum harmonic oscillator, right, the time independent Schrodinger equation let's not talk about that yet. At least I should show the Hamiltonian of the harmonic oscillator system is, yeah, I should at least write down the Hamiltonian first, right? So the Hamiltonian is the kinetic energy operator plus my potential energy operator. And we have shown in chapter 2 that the kinetic energy operator is p squared over 2m, right? And then my potential energy operator, we have now shown that this is m omega square x squared. So this is my Hamiltonian. Okay, so we want to solve a Schrodinger equation where this is my Hamiltonian. So it is not going to be easy, right? Definitely not repeating the same thing that you did in modern physics for Prof. Ong, because he did go through some solution, right? But he did not show the details of deriving it. And the main reason is we haven't learned the bra-ket yet at that time. Now we learn about operators already. So there are two ways to solve the Schrodinger equation now. Now that we know the language of operators and Hilbert space, we can derive the solution using the algebraic method. So this is the first section, the algebraic method. This is, in other words, using operators. Okay, so I believe this is a more fun way to derive, an easy way, less messy. So we're going to do this first. Later, we will show the calculus method of deriving it, which is the power series solution. So there are two different solutions, but obviously they will give you the same energy levels of the harmonic oscillator. So as you recall, right, the energy levels of this system is going to be quantized, and there's a formula, right? So the formula is going to be, we will try to derive this formula, which is n plus half h bar omega, where n is an integer. Start from 0, in fact. Okay, any questions so far? Wait, my clock is not synchronized. It's already 10:47. So 3 more minutes. Yeah, so let's at least separate the variables, okay? And then we will, I will set up the equation and then we will solve it in the next class. So let us look at our Schrodinger equation, right? So this is h is 1 over 2m p squared plus half m omega squared x squared, right? And we'll do the same thing, separation of variables. Okay, so separation of variables is, yeah, so you have already seen this just now, right? During the tutorial, we have went through this, i.e. t over h bar. And then this is the position. This is going to be the eigenstates of the Hamiltonian. So if I plug into the Schrodinger equation, right, I will derive, on the left hand side is I h bar, the derivative of this, you will get minus IE over h bar, E minus IE t over h bar, and then psi, and then on the right hand side is the Hamiltonian. So the Hamiltonian, I'll just keep it in this form first, and then E minus IE t over h bar psi, right? So notice that h bar will cancel, I will also cancel, the exponentials will also cancel, and I will end up with this equation, which is to say that E psi is going to be 1 over 2m p squared and half m omega squared x squared psi. So I'm going a bit fast because we are short of time, but also you have seen this before, right? This is for the special case of the this particular Hamiltonian. I want to simplify this equation. right? So this is the last thing we're going to do. There's a bunch of constants here and there, right? So it's going to be messy to keep on writing the constants all the time. So to simplify this expression for a little bit, I will let E to be h bar omega and this curly E, okay? Yeah, so Jiacheng called this epsilon. This is a big epsilon, curly E. And this P operator, I will let this to be equals to, let me check, be careful with my notes, m h bar omega and then little p square, right? So I will just rescale this operator by this factor, okay? And then this x square is going to be m omega x bar square, okay? So I'm just redefining the operator so that it's going to be more convenient. Why? Because if I plug this in, this is going to be h bar omega e psi, and then on this side is 1 over 2m, and then p square. So I got p square is just m h bar omega p hat square, and then I got half m omega square, and then h bar over m omega x hat square acting on the side. Okay, so why do I purposely define this is because the m will cancel and left with omega on top. So I will have half h bar omega coming out, and then x bar squared psi. And then on the left hand side, h bar omega curly E. On this side, I can cancel the h bar omega, right? So we have reduced into the simple, we now have an eigenvalue equation. Simplified, well, as simple as we can. Which is to say that half p hat square, these are operators, of this, right? So after manipulating, I come to this one is like almost like a simple looking equation. This p, little p and x are not to be confused with the eigenvalue p's, but these are hat, there's an operator. So this operator acting on this state, it will give me, if it's an eigenstate, it will give me the same state again with the corresponding eigenvalues. Okay, so our job in our next class will be to solve this equation, right? So I guess we shall do that next week. We will solve this equation. So we'll do it in the next Thursday, this coming Thursday. Okay, so yeah, this is page 8. I think we ran out of time, but so I know next Monday is going to be the exam, right? And probably everyone will be spending time studying the exam. But for Thursday, I hope that we focus, at least for during the Thursday class itself, we focus on the process of solving this equation. Because well, number one, to me, I think this is a very fun way to play around with operators. It's very intuitive and satisfying, and also pretty smart. And at the same time, if you want to go to, if you are interested in going like theoretical physics, going things like quantum field theory and things like that, that is where we introduce the concept of creation operators and annihilation operators. And that's going to be one of the important basic concepts that will be used a lot later in theoretical physics. Okay. Yeah. So yeah, focus on exam. Yes, we have it on Monday, but the Thursday class is going to be interesting, I hope. So that's all for today. Let me stop the recording.